Good morning. For some people it's morning, for some people it's not, right? All depends on where you are. Yes, see? Dr. Ru, you have people from different time zones. 6 a.m.
Wow.
Yes, so people come from all over the globe. Great. And we have 43 participants here today, and we'll probably get more. Some people are late. You know, Dr. Ru, how it happens with all the meetings.
Yeah.
Okay, I think we are good. So welcome everyone. Today we are going to listen to Dr. Ru. You see his face here. He waves at you. And we're going to talk about multi-messenger astrophysics. Dr. Ru is a scientist at NASA Goddard, and he has an absolutely amazing biography. He decided to be an astronomer at 5. Allegra, please turn off your video. Right. And he visited all possible places on Earth doing astronomy. So today we will learn all about that. So before we start, I want to remind you about our rules for Zoom, right? First of all, for the safety of everyone, please keep your camera and microphone off through the whole meeting. Not you, Dr. Ru, and not me, but everyone else. So you have chat to ask all your questions, and I see all the questions. So don't worry, you don't have to repeat your questions twice. I will see them all. We'll find time to answer them, okay? So please stay friendly and polite to everyone. Everyone means the lecturer, the moderator, and everyone in chat, yes? And please, please don't spam in chat, meaning do not repeat the things over and over again. Do not use capital letters. Don't type in all capital letters, yes? Don't use too many emoticons. Do not annotate on the lecture slides and so on. Please, please stay polite and considerate to other people, okay? So thank you for following the guidelines. And now we will start. So I will stop sharing my screen. Now Dr. Ru can share his own. And I would like to ask Dr. Ru to talk about himself a little bit before he even starts the lecture.
Okay. Good morning, good afternoon, good evening, as appropriate. Julia, if you could confirm that you can hear me and see my screen.
Yes, we can hear you and see your screen. Thank you.
Perfect, perfect. Okay, welcome everybody. Thank you so much for coming. I understand that it's an unusual time you're in many unusual time zones. So thanks for making the effort, and I hope this talk will be worth the effort. I should begin by making a couple of preliminary points. One is, of course, that I apologize that we're doing this remotely because I'd like being able to see your faces and understand the impact of what I'm saying. And obviously, I can't do that. And you don't get to see me jumping up and down and waving my arms about, which is kind of how I usually communicate. So, but we'll do the best we can. So the other major point I make whenever I give this a public talk, whether it's remotely like now or face-to-face, is the role of someone like me has completely changed since the availability of broadband internet. I'm no longer here to give you information. I'll give you some information, but that's really not the main point because all of you are perfectly capable of finding this information online. what I am here to do is provide context, to be able to frame ideas, trends, and maybe clarify concepts that are not, that's less easy to do online by yourself. So with that, I'm going to speak, my topic today is living through a revolution. You may not have realized it, but you're right in the middle of a great scientific revolution. The birth of what is called multi-messenger astrophysics. And if you don't know what that is, you will by the end of this talk. My name is Roopesh Ojha. I work at NASA's Goddard Space Flight Center and the University of Maryland, Baltimore County. I have a relatively pretty new website, which is down there. It's mostly in case you want me to come and give talk somewhere. And on the left is my Twitter handle at Roopesh_Ojha. I put it there because I might not get to all of your questions. And if I don't, then I'll tweet answers at you later on. Okay, so today, this is an outline of what I'm going to do. I've already talked about the purpose of this talk, which is context, context, context. I'll begin by introducing myself, talking a little bit about myself, as Julia indicated, so you'll know the answer to who is this guy. Then I'm going to talk about the first of two completely new ways that we now have to look at the universe, hence the use of the word revolution. So the first new way we have of looking at the universe are these ghost-like particles called neutrinos. I'll talk about them. The other new way is through waves that are produced when very, very, almost unimaginably violent events occur in the universe, creating ripples in space-time, and they are called gravitational waves. So we'll talk about that. And then I'll end by telling you why you should care, why this is interesting. And so let's see how we do. So talking about myself, the picture you see, there are 4 photos. You should be seeing 4 photos. The 2 on the top are part of the Himalayan range. And the highest peak you see, the one on the right is a bit of a close-up, is called Kanchenjunga. And this view is what I saw from my bathroom every morning growing up as a child. That is the 3rd highest point on Earth. It's called Kanchenjunga, and it's about 46 miles from where I grew up. So yeah, I grew up in a very beautiful place. Very importantly, the building you see on the bottom left was my school. I had access to an extremely good school, and perhaps the most important part of it was that it had an absolutely brilliant library. You have to realize that I was born in that age before we had the internet. So we needed actual access to actual books and people like our intelligent teachers to read more. You still need access to books and teachers, but you do have slightly more options than we did. And the other thing I like, the town where I grew up is called Darjeeling. And the bottom right picture shows you a tea plantation. And those ladies are picking the buds of the leaves, which produces the world's finest tea. Because aside from its beautiful views, my hometown Darjeeling is best known for producing the best tea on Earth. While this was a lovely place to grow up, it is not exactly a place where you can learn a lot about astronomy or the sciences. So, but having access to books and good teachers was enough to educate me well enough to eventually get a scholarship to go and study first in one of India's top universities, and then get another scholarship to come and do my PhD here in the United States. For my PhD, I focused on studying one of these objects. And I've shown an example picture up here. I draw your attention first to the bright circle, sort of in the middle of the image. This whole image, by the way, is made using a kind of light called radio waves. Our eyes don't see radio, but this is what you would see if you could see radio, if you can imagine that. So the bright circular thing, which is kind of in the middle of your image, is the area around a supermassive black hole. And I can go into details later. Here I'm just telling you a little bit about myself. And this supermassive black hole eats in a very messy manner. So while it absorbs matter, the matter around it, some of it is trapped by magnetic fields, most likely, and it spews out as a jet. So if you look from the bright circle and you look at the line of light, that's kind of moving towards the bottom left of your screen. That's what I'm calling a jet. It's almost certainly a bunch of plasma, really hot material moving very close to the speed of light. And as you can see, for the most part, it first travels in a straight line. Not exactly straight, because if you look carefully, you can see it's wiggling a little bit, but reasonably straight. And then it gets down close to the bottom of your screen, and then it kind of turns, and there's a really bright spot, and then it kind of becomes like a bit of smoke. It expands into what astronomers call the lobe. Now, if you go back to the bright circle in the middle and look on the other side of the jet, you can see there's nothing, right? It's just like blank. But if you keep going to the top right, there's again some of that woofly structure, like smoky structure up there. And we can talk about this later, but in reality, there is a jet there. We can't see it because of one of the cool effects of relativity. Because these jets are moving at the speed of, or very close to the speed of light, not at the speed of light, the jet that's pointed towards us, which is on the bottom left, gets boosted. Its brightness gets boosted, and we can see it. The one on the going the other way gets deboosted. So we just don't see it in this case. So that's what I studied and continue to study in some cases, these objects, these active galaxies as they're called. The next picture, which should have come up on your screen, shows me at the South Pole. That was my first job. I was running a telescope. Well, first, let me just show you, some of you, this is not a talk of the South Pole, but I'm sure you're curious about how people live and work there. You probably know that the whole year is just equivalent to 1 day at the South Pole. And this is during the 6 months of daylight, and that is the place where we used to live. It's no longer, that's been retired now. There is a newer building. But that was my home, the dome. Some of you might know that at the South Pole, there actually is a pole, the thing that's out there. Of course, the ice is moving, so every year we have to put in another one of those poles because, you know, on January 1st of every year, we put in a new one because the ice has moved, whereas the South Pole more or less hasn't moved, I guess. And that was the telescope that I ran for a year. It studied baby nurseries, big clouds of gas in our galaxy where baby stars are being born. Then I worked with a bunch of telescopes in the deserts of Australia. That's one of the arrays of telescopes I worked with. Then I worked at the United States Naval Observatory. And for those of you who like a challenge, try and tell me in the comments, why do you think it's designed as a circle? You can see it's clearly a circle, the Naval Observatory compound. And last but not least, I ended up at NASA working with this satellite called the Fermi Gamma Ray Space Telescope. That's where I'm at right now. And that's the launch on June 11th in 2008. Our baby is 12 years old now. And having said that, so that's an introduction to me, and I'll be happy to answer other questions about it. So now let's jump into the subject of today's talk. Before I talk about why I use this term revolution and these two new ways of looking at the universe, neutrinos and gravitational waves, let's spend a few minutes talking about how we as a species, or how humans as a species, have been learning about a universe from as far back as we can tell. So on this slide, if you look at the top left, that's from the ancient culture in Egypt. And you see the guy who's sort of arched on the top, the sky god. And then you see the lady lying down at the bottom, the mother goddess. And you find various symbols and hieroglyphs. I put that there to remind you that humans, wherever they were on the earth, were interested in basic questions like where it all began. And apart from, they obviously use their imagination a lot. There's all kinds of stories about where we came from and how the universe was created. And they're really quite fascinating and interesting. But it's interesting to realize that people didn't just use their imagination. They also used their eyes and sometimes some of their other senses to try to see what was going on and then make sense of what was going on. So, for example, very early in human history, people observed the movements of the sun well enough and linked it to the seasons, which was, of course, not just interesting intellectually, but it was really good to know when it was a good time to plant your crops, when was a good time to get ready for the cold of winter, and so on and so forth. So people very early on figured out, notice the sun, because sun is really bright. It has a fairly obvious influence on our daily lives. Pretty early on, people also figured out the movements of the moon. Once again, before you have electricity and other easy ways of creating light, the presence or absence of the moon is very important to your daily life. I actually grew up in a country where many rural areas did not have electricity. So even when I was a child, it was interesting because when I went to a village, people in the villages were very aware of what phase the moon was in. Whereas people like me who live in the city had no idea usually, except people like me who liked astronomy. And then, of course, people, because they could see the impact of the sun on the Earth, they could see the impact of the moon on the Earth in terms of how much light it provides and things like that. It was a fairly logical thing to assume that the stars would also have an effect on us, right? It seems reasonable enough as an idea. So people, went ahead and made up very complicated theories about, how stars individually or groups of stars in constellations would have an effect on us. It turns out, of course, that those ideas are incorrect, and but that's something we learned with further observations. And I say that partly to remind you that it's perfectly all right to use your imagination and come up with an idea. But if you want to be a scientist, you have to explore your idea. You have to test your idea against the facts. And if the facts don't support your idea, it doesn't matter how beautiful it is. You have to let it go. Which is neatly brings me to the second picture. If you stay go to the right of the Egyptian picture, there's a stamp showing Galileo. Um, and Galileo is a perfect example of somebody who used experiments to see if ideas that people had had for centuries were actually true. And he found that many of them were not. So what did Galileo do? Well, he heard about this fancy invention. He didn't invent the telescope. Somebody in Netherlands most likely did. Hans Lippershey is often given credited for it. But he appears to have been the first one to seriously use it to study the heavens. And he made a number of stunning discoveries. We don't have time to go through all of them, but you all know what happened to him. He didn't really have a very good time of it because he got some people very, very upset. And that happens. That's a risk that scientists always run. And I mean, it's true even today. There are a lot of things that scientists find out that our experiments are telling us that some or most people sometimes don't want to know. But you have to find ways, and that's one of the challenges of being a scientist who interacts with the public, is finding ways to explain your results and to explain why they make sense, how much support you have. And that's a whole additional skill you need. So Galileo so up to the time of Galileo, pretty much everything we knew about the universe, we learned simply by using our eyes. And of course, accurate instruments to track, like clocks, for example, have always been a vital element in astronomy. Galileo introduced the optical telescope, which to most people is still simply the telescope, because it's, of course, the most common kind of telescope. And that optical astronomy was pretty much all of astronomy right up until the 20th century. And then you look at the picture on the right of the Galileo stamp, and you see an older gentleman and his son. That's Karl Jansky, and he's one of the people who played a pioneering role in detecting radio waves. That's a different kind of light from what our eyes can see. It has much less energy. And to detect it, you use a telescope. Look at that picture below that. That doesn't even look like what most of you think a telescope should look like, right? It just looks like, I don't know, some kind of scaffolding for construction or something like that. But that is the kind of structure you need to detect radio light, because radio light behaves completely differently than optical light. Okay, moving on. I put a picture there of a satellite. Of course, I picked the satellite that I work for. It could have been any satellite. And the point I was trying to make here is, what we had optical astronomy to begin with. Karl Jansky moved us to the age of radio astronomy. And for a while, we just had those two kinds of things, light that we could study, optical and radio. The next really important step was satellites. Because you see, I will soon be talking to you about many different kinds of light. The trouble is, almost every other kind of light, you can't really study it from the Earth because our atmosphere either absorbs it or changes it in such a way that it loses all its information. So we needed to wait for the invention of satellites so that we could put instruments on them and send them above the Earth's atmosphere. So that's what the satellite picture there represents. The last thing I want you to look at on this slide is the big rock on the bottom left. You'll find me saying every now and then that everything we've known about the universe is brought to us by the messenger that is called light. That's like mostly true. But I put that picture of the rock there to remind you and me that it's not 100% true. There is one other way we've learned about the universe, and that's because we occasionally have big rocks, and sometimes lots of small rocks and dust falling onto the Earth, and they also bring us information. So I just wanted to put it there to remind you that, yes, almost everything we know is through light, but there is that important exception. Okay, so moving on, this is a picture. I will explain it to you, so don't get too worried if it looks busy. The top half of the picture is just a cool cartoon, if you will, of all the different satellites that we currently have flying. Yeah, all of those are still flying. What I really want you to look at is the middle part, where on the left it says radio. Can you see it now? So on the left it says radio, and then you move from left to right, it says microwave, infrared, visible, which is what our eyes see, ultraviolet, X-ray, and then there's a big chunk of it which is just called gamma ray. And then if you still with me, if you go to the right where gamma ray ends, there's a funny picture looking like an upside down tree. That is the highest type of form of light, and funnily enough, we can actually detect that from the ground. So below that, there's a picture of 3 different ground telescopes which can detect light of that very high energy, which is called TeV. It doesn't have a very romantic sounding name. So moving back from the right to the left, you can see, if you look at, below this range of names, radio to gamma ray, if you look below it, can you see the white lines that are drawn kind of coming down to the ground, the cartoon of the Earth below it? Well, when you see the white, if you go all the way to the left again, and where it says radio, to begin with, the white lines are very short. But as you move towards microwave, you can see that they become very long and they actually get to the ground. That's showing you which kinds of light, the radio and the microwave, can actually reach the ground. And then as you move between microwave and infrared, you can see there's like one line which is sort of 1/3 to half the way down, coming to a plane called Sophia. So Sophia is this converted Boeing jet which has a telescope, and it flies high enough that it can see that specific kind of light. It doesn't make it to the ground, as you can see. Then if you can see that with infrared, it doesn't make it to the ground. But then as you start approaching visible, there's a couple of lines that kind of make it to the ground, as long as you're on the top of a big mountain, like the top of Mauna Kea in Hawaii. And then of course it's visible. That's what our eyes can see, and that comes down to the ground. It is distorted, so that's why it's still better to build. If you look above where it says visible, you can see we have Hubble, for example, the famous telescope. It's still worth it to put a telescope above the atmosphere, because the atmosphere allows visible light, but it distorts it a lot, right? So that's why it's still worth it if you want to build a satellite, but we can observe that from the ground, and that's what we have, and we do, that's the most common kind of telescope on Earth. And then as you can see, you go to ultraviolet and nothing. If you want to do any X-ray, if you want to do any gamma ray, look above the line and you see that big constellation of satellites. And that's what we need to observe. So this is how we got here. Some people like me call this the golden age of astronomy, because it's the first time in human history, maybe this happened about 10 years ago, I guess, when we have a combination of ground telescopes and satellites where you can see every kind of light, from the left-hand side radio all the way to the right-hand side TeV. That is a big deal. Why is it a big deal? Well, have a look at this elephant, right? I don't know, some of you might already know this story, but bear with me, I'll tell you the story one more time. in this picture, it shows 6 people who were born without being able to see anything. So they decide that they want to know what an elephant is. So they're brought to an elephant, and I'm sure it's a tame elephant because it doesn't complain about people coming up and pulling its tail and touching it, something that I would not recommend you try with almost any real elephant, actually. But they come up to it, and as you can see, the guy on the leftmost, he's holding the elephant's ear, and he says, "Hey, that feels like a mat." Then the guy next to him is holding the elephant's trunk, and he concludes that an elephant is like a snake. The other guy, the guy to your right, is touching the elephant's tusk, and he says, "Wait a minute, the elephant is like a spear," and so on. The point here is, of course, that none of those guys is completely wrong about what an elephant is, and none of them are completely right either. They all know one small piece of information, which by itself is very limited. The only way they can figure out what an elephant is really like is if all of them sit together and combine the information. Then they might be able to figure out what an elephant is like. And that is precisely what happens with astronomers. So these are all the different kinds of light. You already saw the previous slide, they were represented in a different way. You have radio waves, which have the lowest amount of energy. And then as you move to the right, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays, and TeV rays. All of these kinds of light bring you information that is unique. So you need, if you really want to understand anything, even something you think is very familiar like the sun, you really need telescopes at all of these wavelengths. And then you need to be able to put the information together, just like the blind man and the elephant.
Doctor, we have a couple of questions that were asked here. One is, what was used on Voyager? What spectrum Voyager was studying? And another one is, do we have anything to observe dark energy?
Okay, so Voyager, I don't remember the exact range of wavelengths it was studying, but I think it basically covered the optical and parts of the infrared and UV and of course radio. And of course it has a great antenna, which is why we've been able to track it, as I'm sure you know. Nowadays, most exciting thing about it is that it has left our solar system. Do we have any way of detecting, did you say dark energy or dark matter? Sorry.
I think people ask dark energy. Mm-hmm.
Okay. Okay, let's put it this way. No one's detected dark energy yet. We have a number of different experiments that are trying to detect dark energy based on what people think dark energy could be. It's really important to realize, especially if you're a young person, which I presume you are when you ask this question, that we don't actually know for sure what dark energy is. And if you don't know what something is, then of course it's hard to design an experiment to detect it. If you don't know its properties, so how will you detect it? So I guess the answer to your question is there are at least, that I know of, 6 or 7 different ways people are currently trying to detect dark energy. And so far, no one has a detection that's really confident. I hope that answers your question. If for dark energy, you have to keep thinking, what is it? What is dark energy? And based on, if you have some idea what it might be, then you get to detect an experiment. Design an experiment to detect it. Should I move ahead, Julia?
So they're asking, if you are looking for dark energy, how can you look for it? So that was more or less, I think you more or less answered that.
Yeah, you have to decide what, I mean, so most of the theories about dark energy is postulate the existence. They guess that there are particles, which are exotic particles, not obviously particles that we are familiar with. And then they have to guess what the properties of these particles are. And then the experiments try to look based on those postulated properties. You know what? When I talk about neutrinos, I'll give you a really good example of how this process works.
And probably one more question here before we move on. People ask, do objects in space generate more radiation than objects on Earth?
Okay, so the amount, did you say radio or radiation?
People asked about radio. I think radio waves. That's what they're asking.
Radio waves. Okay. All right. So radio waves are produced. The thing is, when you say objects in space, the objects that we are detecting are enormous, right? So it's probably not fair to compare them. I mean, the Earth itself is very small compared to something like the sun, which is not even all that bright in radio, but it's, you know, it's bright. So I'm not sure you can make a fair comparison because anything we have on Earth, Earth is tiny. In the big scale of things, the Earth is tiny, and everything that, and you know, so the objects that with my telescopes, I'm studying, they are the size of the entire Milky Way. So of course they produce a lot more radio waves. But I mean, so I don't know if that completely answers your question. But yes, I mean, the sources of radio energy on Earth, though, are a lot closer, right? So if you have a simple radio, you know, a simple radio emitter on Earth, it is going to, you are going to receive a lot more radio energy from it because just because you're closer to it. So, I mean, most of the objects that I study, if you were actually close to those galaxies, then of course there'd be very, very intense radiation, right? But because they're so incredibly far away, by the time those radio waves, the little tiny energy that reaches us, that is really tiny. And that is the reason why we keep building bigger and bigger radio telescopes, because the objects, you know, the bigger we build, the more sensitive they are, and we can detect objects that are fainter. But yeah, it's important to remember that these objects are not really faint. It's just that they're so far away that they appear, by the time their waves get to us, they're very, very weak. So, you know, with all these things, there's a question of how strong they actually are, but there's also a question of how far away they are.
Yes.
Okay, so so moving ahead, the main thing that's happened in the last few years, the reason why I keep talking about the word revolution is look at this picture that's in front of you right now. This is all the different kinds of light, and these are all the kinds of, we call them messengers because they bring messages to us from the rest of the universe. Now, the world you live in, since about, I don't want to put an exact date in it, but say around 2013, 2014 onwards, we have now got the capability of detecting neutrinos. And, you know, and if you look at what it does is it essentially increases greatly the range of energies that we can probe in the universe. Okay, so now let's jump to the two new messengers that humanity has acquired. So remember, so before about 2012, 2013, everything we knew about the universe, the messenger was light. Now we have two new messengers, and the first one I'm going to talk about is a neutrino. So what is a neutrino? Well, a neutrino is an extremely light particle. We don't know exactly how heavy it is, but we know that it's very, very light. So light that it's almost massless, not quite. One of the things that I find most fascinating about the neutrino is it doesn't talk to anybody. It doesn't interact with anybody. And that's why I put that little cartoon there, because I like to think of the neutrino as a snob. And there are so many neutrinos that about 65 million of them pass through your thumbnail every second. Right now, as all of you are sitting or standing wherever you are, there are literally 65 million, I mean, there are trillions of them going through your entire body, and they'll go right through you, they'll go right through the Earth and out the other end and keep going because they hardly ever interact with anybody. So what that means is they're very hard to detect. And I don't have time to go through the whole history of it, but this is a picture of what used to be my home for a while. This is the South Pole, Amundsen Scott South Pole Station. Obviously, it's an aerial shot. And it's an old picture because it still has, if you look at sort of the middle to the left, you see a silver-colored long building. That was, you might recognize that. That was my telescope. That's where I used to work. And you see a cone-like thing next to it. That's where there used to be a instrument, a telescope trying to observe small variations in the cosmic microwave background radiation. And then if you go sort of to the right, you see a jumble of little huts. There's no telescope there above the ground. Because neutrinos are so hard to detect, the telescope that detects them, that has done most of the detection so far, is it uses the ice itself as a detector. So because it's under the ground, I can't take a picture. No one can take a picture. So I'll have to show you a diagram. Okay, so that's sort of what it looks like. On the top, you can see that it says ice top near the top of the picture. Then you see those little lines coming down. They call them ropes, but they're really wires. They carry electricity and signals down and up. And if you go down, you can see, like, the top part of the ice, there's nothing. There's just the ropes, as they call them. And then when you get below a certain depth, then at intervals, they have, if you look on the left bottom, it says the digital optical module. Those are like these spherical instruments, and they are at regular intervals. So they form like a three-dimensional lattice. And then what happens is, if a neutrino comes in, so in this case, in this diagram, when the neutrino is coming in from the left of the diagram. And most of the time, of course, nothing will happen. Like I said, there's billions of them going right through you and right through the earth, and nothing happens. But because this is a cubic kilometer of ice, so I kind of forgot to mention that. So if you look at this figure, the part that has the instruments is about a kilometer wide, deep, and long. So in this cubic kilometer of ice, you have billions of ice molecules. And there's a small chance that once in a while, a neutrino actually collides with one of the ice molecules. When it does that, it produces a particle called a muon. And that travels through the detector very close to the speed of light, and it produces a different kind of light, which is detected by those digital optical modules. And so that's how you detect neutrinos. Now, what is so great about neutrinos? You've seen that they're kind of a pain because they're very hard to detect. And you have to go and, I can tell you about later. I was there when this instrument was being made. It was lots of fun because, it was the only place in Antarctica where you had hot water. You could actually have a bath. Which were very
Dr.
quick.
Roo, we have a couple of questions about
Okay.
neutrinos here, if you don't
Of
mind.
course.
So the question is, if there is a very large number of neutrinos that are passing through a very narrow space, what will happen?
Okay, so basically, very narrow space. So the probability of a neutrino, any individual neutrino, interacting with any individual particle is very, very small. So when you say narrow space, you haven't told me if you have a lot of particles there. So for example, if that narrow space is an interstellar space, then your chance of the neutrino interacting is very low, right? Because there's not a whole lot. I mean, interstellar space is very close to being a vacuum. So in that case, you have very, very, very even lower probability of detecting the neutrino. But if you say that little narrow bit of space is like the ice in Antarctica, okay, then you have a slightly better chance of detecting a neutrino. So it's not so much how narrow or wide the space is. It has more to do with how many potential target molecules are packed into that, right? Are there any other questions?
Yes. What happens when a neutrino collides with another neutrino?
Ah, that's a brilliant, brilliant question. I don't know the answer. I don't think anyone does. We've never, to the best of my knowledge, we haven't really observed anything like it.
So people ask whether it's just our matters that neutrino doesn't interact with. Is there any other type of matters that the neutrino will be willing to interact with?
Wow, that is a really good question. So let's begin by saying we only really know what happens with neutrinos with the matter we are familiar with. And as I've already said, it interacts extremely weakly. It's very rarely with the matter we know. Now, I think somebody was asking about dark energy, for example. Well, some of the candidates remember that there are a lot of theories about dark energy, okay? There are literally dozens of theories. And I believe that some of the postulated candidates for dark matter are supposed to interact better with neutrinos than the regular matter, baryons, or the matter that we are familiar with. But so theoretically, there might be some other matter, but right now we have zero evidence for any of this. But it's really fun to think about, and it's something that we should think about in a way. Well, it's good to work out the math and see if there's a way we can test for it experimentally. You'll keep hearing me say that because I love being imaginative, and personally, I love being imaginative and I love working out the math. But I get particular satisfaction in seeing if I can detect something experimentally, because that's that's when I at least feel like I'm doing real science.
A couple of more questions here.
Sure.
What makes neutrinos so non-interactive?
That's their nature, I guess. I mean, yeah, I don't know how better to answer that question.
And the continuation of that question is it possible for us to change our matter to be less interactive?
Change our matter. Unfortunately, there's very little we can do to change what we are made of. I mean, it's not, like many of you probably have heard about historically, humans have always wanted to do this, right? I mean, and in some ways you could argue that that's what chemistry is. That's what certain kinds of physics is, right? I mean, you take substances and we change their chemical properties, we change their physical properties. So in that sense, we do that. But at the fundamental level, at the level of, the elementary particles that we're made of, I certainly don't know how to make any changes. And in some ways, your question reminds me of what used to be called alchemy, where people spend a lot of time and experimentation trying to take a substance, usually what they call a base metal, and tried to convert it into a valuable metal like gold. And yeah. So while we are able, and in every single day we manipulate materials around us. I mean, that's what makes our lives easy and comfortable, or even possible in many cases, right? We create new materials, we change their physical and chemical properties. At the fundamental level, yeah, I don't know of any way to change basic materials. And again, I like to stress that just because I don't know, and just because it's not done at the moment, does not mean that it's always going to be impossible to do. So as a young person, if you want to think about how to do that, I would definitely not stop you.
And people have lots of questions about neutrinos. Right. Will you take some more?
Well, it's 12:44. Do you want me to just people are very interested in neutrinos. So let me say a couple of words about gravitational waves, and then we can just do questions. Would that work?
Sounds good.
Okay, because I just want to mention it at least. We want, obviously this like I said, I really expect you guys to follow this up by, they're really excellent places where you can learn online, and you can shoot me questions and I can guide you to some of those places. But I did want to mention that just like neutrinos are a completely different way of learning about the universe, the other new way of learning about the universe that we've sort of started to learn how to use, and the first successful detection, by the way, was in 2015, and by one of those interesting coincidences, it was the 100th anniversary of the prediction of gravitational waves, by Albert Einstein. So that was kind of neat. So gravitational waves are literally distortions in space-time. They're distortions in the fabric of space-time, and they're very, very, very small. The changes that we're looking for here are so incredibly small. They're much smaller than the size of an atom, right? So this, in addition to being cool scientifically, to me, what's amazing about this, and actually also about the neutrino detector, is the engineering here is absolutely mind-blowing. So I want you to look at these two aerial shots of two L-shaped detectors, right? One of them is in in Washington State. Those of you know your US geography. And the other one is in Louisiana, which is sort of the southern end of And both of these are what are called interferometers. So each of those arms, the two L-shaped arms, there's a beam of there's a beam which is shot down that arm, and in the central building, the two beams interfere and create what's called an interference pattern. And then when a gravitational wave is actually detected, when the pattern shifts very, very slightly. This is a whole talk. This is several talks. So that's all. I just want to give you a flavor of how it is done. And the very first detection, the physics behind this is surprisingly well understood. I say surprisingly, given how small these displacements are. And the very first detection that I mentioned was people were able to calculate that it was two black holes, 29 and 36 times the mass of the sun. They came together, they collided about 1.3 billion years ago. And here's one of the things that I find still, I say this all the time and I still find it hard to believe. 3 times the mass of the sun was converted into gravitational waves in a fraction of a second, which meant that the peak power output was 50 times that of the entire visible universe. That's not a typo. It was 50 times that of the entire visible universe. I just wanted to quickly mention that the math here has been worked out so well in advance that those two graphs that I'm showing you, you don't on the on the y-axis, it's just something called strain. It's a measure of how strong the distortion was caused by the gravitational wave, and on the bottom line it shows time. And you look at the shape of the two squiggly things. One of them was at the Livingston, the detector in Louisiana, and the other one in Washington. And to a very good approximation, the two wiggles are almost exactly the same. They're not exactly the same. If you look really carefully, you'll see slight differences, but that's measurement noise. So I always find it remarkable that we know the math so well that and it's really lovely to see an experiment confirm that. That's it. I did want to say that when I first started giving this talk, I was going to compare the car on the left to electromagnetic, to light, and the two flashy-looking cars on the right, neutrino and gravitational wave astronomy, and say that, oh, those are the cool new things. But then I realized that this is actually completely incorrect. This is totally incorrect way to talk about it. So then I realized that the more correct way to talk about it is the yellow car on the top. That is more representative of electromagnetic or light astronomy done by light. It's in very good shape, it's solid, it's very reliable, and it's, as I said, we're in the golden age of astronomy. The neutrino and gravitational wave astronomy are like the two babies that you see at the bottom of the picture. They look healthy. They will almost certainly go on to do great things. But at this point, it's too early to say, at least for me, exactly what they will reveal to us. Just like with a baby, you don't know what they're going to grow up and do. You can tell, though, that they're healthy and they'll grow up and do great things. So I will take questions, but I'll leave this slide up because I often end these talks by chatting about why you should care. Why do we even bother building such complicated and, let's face it, expensive experiments like LIGO, the gravitational wave detector, or IceQ, which is the neutrino detector I showed you? But that we can deal with that if you're interested later. I'll stop here and I'll be happy to take questions for the rest of the time we have, Julie.
Okay, we have lots and lots of questions. So here we are. Do neutrinos generate gravitational waves?
No. Well, at least, so gravitational waves are extremely, so gravity is one of the 4 fundamental forces in nature. It is the one that dominates the universe. But curiously enough, it's actually the weakest of all the fundamental forces, okay? You need a lot of matter, a lot of mass to have significant amount of gravity. I'd like to remind you, wherever you guys are sitting, okay? If you have, do you have something in your arm's reach? Can you hold a pencil or a pen for me or whatever you have near you? Now go ahead and lift that pencil, okay? Are you doing that? Well, guess what? You just won a tug of war with the Earth. You had the entire gravitational attraction of the Earth on that pen or pencil or whatever it was that you picked up. And the energy of your one arm, or maybe just your finger, was strong enough to beat all the gravitational force of the entire Earth. So you have to remember that gravity ends up winning in the universe because there is a lot of mass in the universe. But gravity is an extremely weak force. And gravitational radiation is extremely weak, extremely weak. And neutrinos, of course, are almost massless. So, so yeah, that's not something, that's not like a something that we are anywhere close to being able to detect. We can barely detect gravitational waves from objects that are the size of several times the mass of the sun colliding violently.
Another question. When a neutrino and antineutrino collide and inevitably annihilate, is there any energy generated or heat or nothing?
Energy. You end up with some energy.
So, and people ask whether it's a lot of energy or just a little compared to other particles.
It's really not much.
What is the best source of neutrinos? Where
Well,
do they
okay,
come
so neutrinos. One thing I haven't had a chance to talk to you about is neutrinos have a range of energies. So the neutrinos that I've been talking about mostly, and the kind that IceCube has been detecting. Sorry, these are very high energy neutrinos, and we you must be getting tired of hearing me say this, but we don't know for sure what produces them. Um, uh, my group, our research suggests that at least in some cases, they are produced by jets in active galactic nuclei. Do you remember the picture I showed you of that jet, the relativistic jet, which is coming out from near a supermassive black hole? Well, there is some evidence that at least some of the really high energy neutrinos are produced by those jets in AGN. But that's the really high neutrinos. One of the fun things that I like to point out is that there are lower energy neutrinos that we know are produced by our sun. So the process of nuclear fusion, which powers our sun, of course, naturally produces neutrinos, but they're still, they're pretty energetic, but they're much lower energy than the neutrinos that are produced that the IceCube detects. So the sun produces some neutrinos. In 1987, we were able to detect also neutrinos from a supernova explosion, where a star basically just dies a very violent death. What's even more cool, I think, is I don't know how many of you recently ate a banana. So bananas have potassium, and the potassium, a certain fraction of the potassium in your banana is going to undergo naturally, completely naturally, radioactive decay, and that produces a very low energy neutrino. So anytime you peel a banana, you are actually, being hit by a few neutrinos, which are very, very low energy. So there's a range of neutrinos of different energies, and they're produced by, as I just gave you a few examples. Radioactive decay of potassium produces very low energy neutrinos that, yeah, and the next time, you will never eat a banana again without thinking about the fact that you just released some very low energy neutrinos.
So another question, can neutrinos get together to organize some type of structure?
Not as far as we can tell. So yeah, I mean, yeah.
So no glue between neutrinos, no
Yeah,
glue forces.
yeah. I mean, it's a very good question. It's just that at the moment, what we understand of their properties, it doesn't look like something we can do.
What is the photo with the phones here on your slide?
Oh, what's the photo with my phone? Oh, good. I'm glad you asked. So it's a good question to ask why we bother studying all these things. And of course, like for most of you, like me, the answer will be, well, it's just cool. We don't really care. But but like a lot of these projects are extremely expensive and time consuming. So you have to sometimes answer this question that, hey, why should the government or some wealthy individual give us a lot of money to go and do basic research, okay, to learn about exotic things like gravitational waves and neutrinos? And one of the answers is that I put up a word there, serendipity. And that just means that you discover things by accident. And that happens time and time again with when you're fooling around doing basic science. And that cartoon there with the camera phone, of course, is referring to the fact that I think virtually all of you, if not literally all of you, have a smartphone. And of course, a smartphone is a camera and it's also a phone. It's also a lot of other things, actually. And so the cartoon just making fun of this guy who's made a camera phone and his cat is saying it'll never catch on. The joke being, of course, that of course it's caught on. Every one of you has one. And that's just one of the reasons, one of the very important reasons. I mean, if you look above the camera phone, I don't know if you can tell, but that's a sonogram picture of a baby, and uh, I, like I started doing radio astronomy, and we make images that are very dirty. And some of the algorithms that we developed, that a number of people developed to make those images cleaner, later on, the same algorithms were modified to make images of sonograms cleaner. Now, those of us who are studying radio galaxies and active galactic nuclei, none of us was thinking, oh, one day we are going to use, this is going to be useful to produce better ultrasound images. That never occurred to anybody as far as I know. But later on, by accident, someone realized, hey, wait a minute, the same algorithms that can clean our pictures of radio galaxies can actually help to make better sonograms. So that's an example of what serendipity. And it's one of the reasons why doing basic science is a good investment.
So a couple of more questions here. One is, do neutrinos travel faster than light?
So nothing travels faster than light that we know of. And the way to think about this is light, as I said, neutrinos are very, very close to being massless, but they do seem to have some mass. And the moment you have mass, you cannot reach the speed of light. So neutrinos are very fast. They travel very close to the speed of light, but they cannot reach the speed of light because they have a little bit of mass.
And the last question probably that we have here is, what are you working on right now at this moment, and what do you like the most about it?
Right. So, okay. So probably the most exciting thing I'm working on is something I briefly mentioned to you. I'm trying to figure out where the highest energy neutrinos that IceCube is detecting, where they are born, where they're coming from. And as I said, my group found some evidence that they were coming from the jets of some AGN. But then you have to ask the question, well, why are they coming from some AGN and not from all AGN? What's so special about those AGN? So I'm doing a series of experiments where I'm trying to understand the physical properties of AGN and trying to identify why some of them will produce these neutrinos and others don't.
And
So
what is IGN? Just a second.
Oh, active galactic nuclei, the kind of thing I showed a picture of, a galaxy with a big supermassive black hole at the center, which is eating a lot of stuff, but it's also spilling out stuff in jets. Mm-hmm. So that's probably the most exciting thing I'm working on at the moment. And it's exciting because we're doing something completely new, right? I mean, this is what you get into science to do. You poke around and you try to find a good mystery, and when you've got it, and you have the tools to solve it, that's why we get into this business, right?
Okay, yeah, sounds extremely interesting. Like you actually learn something where we cannot touch it, we cannot send anything there, it's so far away, but we can still learn about it. So we can,
So just Julia, before we end, I should say that if your question didn't get answered or something, you can probably type it, send it to Julia or type it. And I am on Twitter at Roopesh_Ojha. Remember, it's
can you type it in chat, Dr.
Sure.
So everyone will see it, and I will make a mistake.
So any good question, I will promise to tweet the answer back at you, and I should be able to also include like a link to a picture and explanation. So that's my yeah.
Okay, well, thank you so much.
Thanks everyone for your patience, and I hope you'll have a lot of fun. And you guys are born at such a great time, honestly. It's not like and I mean, there are certain times in human history. It's like you're being born at the equivalent of somebody born when Galileo had just figured out how the telescope worked or something. So if you choose to study this field, I think you have tremendous potential. Okay, I should stop talking and say, wish you all of you goodbye. Thank you for having me, Julia. Thank you everyone for coming.
Well,
Bye now.
thank you for sharing your knowledge and your time with us.
You're welcome. Bye-bye.
It was extremely interesting. Thank you so much. Goodbye, everyone, and send your questions to Dr. Ru if you have them, right? Goodbye. Thanks. And come again, we have more interesting webinars. We have another webinar next Friday, when we are going to learn about what's inside the Earth, right? Okay. See you next week. Goodbye.